All right, guys, in this video, we're going to go over some electron configuration. We'll see a few practice problems on that. So here's one. We got, what is the ground state electron configuration for the sodium plus ion? Okay, there's a few key parts that are important. Okay, so we are looking for electron configuration. So remember, we're looking for the orbitals, 1s2, 2s2, 2p6, and so on and so forth. Ground state. Ground state means that there are no excited electrons. Everything is going to be in their lowest possible subshells. There won't be an excited state, which means that there's an electron in a higher subshell. So next thing that we need to know, we are looking for sodium plus. Now sodium by itself, if it was in a neutral state, should have 11 electrons. But since we have a plus, that means we have lost an electron, we've given it up, or something has happened to it. So really there's only 10 electrons in this ion. So I need to write an electron configuration that fills up 10 electrons in the first set of subshells. So in the lowest subshell, it is 1s, and it will occupy 2 electrons. The second subshell will be 2s, and it occupies 2 electrons. The next subshell is 2p, and that would occupy, we can have up to 3 shells in there. We got 1, 2, 3. I've now used 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's my 10 electrons, 2, 4, 6, 8, 10. They have filled all of the 1s, 2s, and 2p orbitals. So that means my electron configuration would be 1s2, 2p2, or sorry, yeah, 2s2, sorry, 2s2, and then 2p6. And this would be the electron configuration for Na plus ion. Now that was all extra work that you do not need to do. As long as you know you have 2 electrons, you can start writing out the electron configuration. Remember these subscripts on the top, okay, those represent the amount of electrons. So as long as you do enough to get it to 10, you're going to get it to the right configuration. Okay, here's a little more complicated question. We have a new element with an atomic number 116, which was discovered in 2000. In 2012, it was named livermorium, LV. Although livermorium is radioactive and short-lived, its chemical properties and reactivity should follow periodic trends. So, question A, write the electron configuration for the valence electrons of LV in ground state. So a couple things. We're looking for the valence electrons, that its electron configuration, and it's also in ground state. That means we don't have any excited electrons. Okay, if we look over at LV on a periodic table, if you don't have one, that's okay. It is on the 7th row, and it is in our p orbital column, an area. It is in the 7th energy level because it's in the 7th row. It's in the p orbital status or area, and it is 1, 2, 3, 4 electrons for its ground state. So its electron configuration for the valence electrons, we have 7p4, and we should also have 7 s2. So these are the 6 electrons in their valence shell, and that would be the electron configuration for those valence electrons. We have 2 electrons in the s shell and 4 electrons in the p shell. Okay, so that would be just for those valence electrons. And B, the first ionization energy of polonium, PO, is 812 kilojoules per mole. Is the first ionization energy of LV expected to be greater than, less than, or equal to of polonium? Justify your answer in terms of Coulomb's law. So polonium, PO, is 1 element higher on the periodic table than LV livermorium, okay? Which means the valence electrons, I'm going to do a rough sketch. So if this is LV, okay, polonium's valence electrons will be slightly closer to the nucleus. LV is going to be a bigger element or a bigger radius because it has extra subshell. This goes to a 7p4, whereas polonium goes to a 6p4 as its valence electrons. So due to that, polonium I would expect to have a greater ionization energy than livermorium, meaning polonium's going to hold on to those valence electrons a little stronger than livermorium, and that's because those electrons are actually going to be farther away. So when we need to justify your answer in terms of Coulomb's law, I would say polonium has a higher ionization energy than LV livermorium. Polonium has a smaller atomic radius, and therefore the nucleus has a higher nuclear charge than LV. Due to that higher nuclear charge, the electrons in PO are held more tightly and therefore have, or I should say, therefore polonium has a higher ionization energy. Okay, now that seems like a lot. I did a little bit of a claim right here. Okay, I state that polonium has a higher ionization energy. Here I give my reasoning, and here I explain why ionization, so evidence basically. Okay, or evidence then reasoning. I switched those. Whoops. Evidence and reasoning. Okay, so that just breaks it down all together, brings it all nice together to answer that question. So lots covered in this video.